Greetings, student. Let us continue your education after that exhilarating educational video. Now, being that you've done all your work on the worksheets, you would be aware that after the Big Bang, 75% of the universe was hydrogen and 25% was helium. And these big gassy clouds expanded over the universe like a great fart of the Big Bang, and they came together. As you'd be aware, gravity exists between particles with mass, so they attract each other, and over time these clouds of hydrogen and helium got closer and closer and closer together, to the point where the friction was so great from them coming together that there was sufficient energy to cause the fusion of hydrogen. Now, how do you make helium? Now, one possible way is to do as you'll see in the following video. 1,1H plus 1,1H gives 2,2He. It is definitely helium. It has 2 protons. That is helium. It has an atomic mass of 2, but it has no neutrons. This cannot work. So what we saw there was 1,1 hydrogen plus 1,1 hydrogen to make 2,2 helium. Now, of course, that is definitely helium because it has 2 protons, but it is not a molecule that can possibly exist. You might remember from my previous conversations that there are 2 forces which are in a fine balance in the nucleus of an atom. The strong nuclear force, which is between the neutrons and the protons and the neutrons and the neutrons, and Coulombic repulsion, which is the positive protons pushing on the other positive protons. Now, when an isotope in an element is stable, i.e. it doesn't need to radiate to achieve a lower energy state, those 2 forces are in balance. But often they're not. Now, in the case of 1,1 hydrogen with another 1,1 hydrogen fusing to become 2,2 helium, it's not actually possible for that to form because the 2 protons would push on each other and there's nothing to provide strong nuclear force to balance it. So those 2 protons would never be able to come together. When you look at these situations, there are only a couple of possible pathways by which you could make this stuff. So how do we make helium out of protons? Well, we need to have a source of neutrons. The neutrons must come from somewhere. If they don't, then there's nothing to provide strong nuclear force. And you'd note that 4,2He, helium, has 2 neutrons and 2 protons. So where do the neutrons come from? And the answer is positron emission. Have a look at this video. Proton becomes neutron, which is going to be 1 and 0, and that's going to be plus beta positive, which would be an electron, so that's going to be 0 and 1. Noticing that that's positive 1 because it's a positive electron, plus a gamma ray, plus a neutrino. A proton will actually become a neutron, what we call a positron, or positive electron. Note that when I write the E, it's actually a plus 1 as opposed to a minus 1, a gamma ray, and what we call a neutrino. Now, this whole neutrino thing, everyone thinks, well, what are they, why are they there, etc. and so on. The reason that we know they exist is because when scientists looked at the emission of electrons, for example, from an atom, and they looked at the emission of a positron, a positive electron from an atom during nuclear radiation, and they looked at the final energy of the gamma ray, because that's just an electromagnetic wave, it's just up the far end of the electromagnetic spectrum, so it's got really high energy. And the positron or the electron, even though we do tend to treat them as massless, they actually do have a mass. If you look up at the stage 2 physics worksheet on the board, you'll notice the weight is 9.11 by 10 to the negative 31 kilos. So that will come out at a certain energy, and because it's got mass and it has energy, it can have kinetic energy. and it'll have a certain amount in joules. And then you've got the neutron, and they looked at all of this stuff and they thought, well, with the neutron, the beta plus or minus particle, and the gamma ray, there's energy missing. There's something that's missing out of the picture, and so they posited the existence, they thought of the existence of the neutrino and since discovered them. They are a particle. I'll read straight from What is a Neutrino? Neutrinos are one of the fundamental particles which make up the universe. They are also one of the least understood, especially by Mr. Turley. Neutrinos are similar to the more familiar electron with one crucial difference. Neutrinos do not carry electric charge. Because neutrinos are electrically neutral, they are not affected by electromagnetic forces which act on electrons. Neutrinos are affected only by the weak subatomic force of much shorter range than electromagnetism, and are therefore able to pass through great distances in matter without being affected by it. If neutrinos have mass, they also interact gravitationally with other massive particles. But gravity is by far the weakest of the four known forces. 3 types of neutrinos are known. There is strong evidence that no additional neutrinos exist, unless their properties are unexpectedly very different from known types. Each type or flavor of neutrino is related to a charged particle, which gives the corresponding neutrino its name. So you've got one called an electron neutrino, and they're the ones that we're concerned with. When you have a positron emission, you get an electron neutrino, and when you have a electron emission, you get an antineutrino. Now the thing is that these things fly through matter, billions and billions and billions of them. And I was listening to a scientific podcast the other day, and they said that if you hold your thumb in front of your face, the thumbnail there, 6 billion neutrinos pass through that thumbnail every second. Now how the hell do we detect them? Well, we've got massive, massive labs underground that detect them. At the end of this podcast, I've got a couple of videos there that you can watch that relate to neutrinos, just for interest. So, because we're able to detect neutrinos, we are actually able to confirm the existence of these, fusion reactions that occur in the sun. Because it's not like you can just go to the sun and go, "Hi sun, I'm Adam," and open it up and go, "Ooh, look at your fusion reactions." Because the sun's, well, it's hot, it's got a gravity 26 times that of Earth, and there's no air in space, it'd be hard. So you have to look at the stuff that comes out of the sun to make any sense of it. And of course, one of the things that blasts out of the sun continually are these neutrinos, which confirm the pathway by which neutrons are made. There are other things that you can look at too. For example, how do we know that hydrogen is becoming helium in the sun? And that's done through that spectroscopy stuff. When you get light from a particular element, that element has electron orbitals. And the electrons can be excited up to higher orbitals. They're like rungs on a ladder. If you step between the rungs on a ladder, you'll get no purchase with your foot and you'll fall straight through. Well, the same exists for electrons. They can only exist at set energy levels. Any of you who are chemists would know you can do 2 electrons in the first shell, then you can do 8, and then 8, and you go on from there. And as you add every extra electron, it adds an additional energy level. Well, it turns out that you can jump electrons up a couple of energy levels, and then they'll drop back again, and release specific wavelengths of light related to that energy difference, that gap. And that's what we call an emission spectra. But, as it turns out, the outside of the sun itself has an atmosphere. Not one that you or I could breathe, but it's there. And in it aren't big, hot, thermally motivated particles releasing light of all descriptions because it's a hot particle that's vibrating. It's actually a gas which is a bit cooler, and it will absorb certain frequencies of light that are related to that energy level which is aligned to that element. We call it a spectral fingerprint. Every element has its own spectral fingerprint. And as a result, we look up there and we can say, wow, okay, there's these Fraunhofer lines, and they mention that in the video, and they confirm, because they line up with the Fraunhofer lines for hydrogen, then we know there's hydrogen there, and there's helium there. And we can tell what different elements are there. That's how you look at starlight and you're able to determine the elements. So that's also proof for us that these reactions, these nuclear fusion reactions, are occurring in the sun. Now, once we've got these neutrons present, we can start to actually cause neutron capture by a proton in the sun. So a hydrogen goes along, captures a neutron, and becomes 2,1H or 3,1H, deuterium and tritium. There are three isotopes of hydrogen that you need to know. The three isotopes of hydrogen: 1,1H, protium; 2,1H, deuterium; and 3,1H, tritium. And these are the ones. You have deuterium 1,1H, protium 1,1H, deuterium 2,1H, and tritium 3,1H. So the deal is that protium, which is 1,1H, has no neutrons. Deuterium has 1, and tritium has 2. And they're sort of called heavy hydrogen. Now, if you get two deuteriums and smash them together, you get 4,2 helium. Note that up the top, the two 2's add up across to the other side and become 4, and that is because the number of nucleons align when you have a transmutation reaction. Remembering that nucleons refer to both protons and neutrons. The mass numbers are conserved. And if you look down the bottom, 1 and 1 becomes 2, so the number of protons in this case are also conserved. But that's not the only pathway to make helium. There's another, and that is you can get 2,1 hydrogen, so your deuterium, smash it together with a protium, and you'll get 3,2 helium, which is an isotope of helium, and one that's not extremely stable. Now if you get a couple of those 3,2 heliums and smash them together, then you get a 4,2 helium and 2 protons, which can go off and do their proton-y thing again. And of course, when you've got a sun, which is infinitely hot and all this stuff smashing around in there, well, these kind of reactions occur. And the deal is that each of these reactions, when they occur, releases a crap load of energy. Mountains of it. That's why the sun is so hot. And even then, it's not the hottest sun. There are many more that are hotter than it. Now, you might be aware that a sun will produce different elements relative to its mass. And the highest element in the periodic table that you can generate from forcing nucleuses together in the core of a sun is iron. Anything above that requires a supernova, i.e. when a star just basically explodes with such force that it generates all the heavier elements. So if you think of something like uranium-23592, all those fuel rods, we're actually like gathering the result of supernovas, refining them and sticking them into a nuclear power plant to generate electricity. And that power was originally stored in those nucleuses by a supernova eons ago. It's like that question you could ask any carbon atom in your body: what is your story? And it would have been created in a sun somewhere in the universe, in the known universe, and travelled through eons of space and time. It would have gone through countless different bodies and cycles and somehow ended up in you. So, you know, there are carbons out there that have been generated from the wonder of the Big Bang, traversed the eons of space, condensed into a planetary body, gone through all the formation of the land and the seas and the life coming out of the ocean and this great evolution of species, so that someone can go, yeah boy, for over 1:30.
Yeah boy! Yeah boy! Hot and spicy meat. Yeah boy!
And you wonder why I lose hope in society. Yeah boy. So, where do we go from here? Well, we know how to create carbon now, which is fantastic. And by the way, I'm going to add, this is called the triple alpha process, where you go from 4,2He to 4,2He, and you make 8,4Be, which is beryllium. And once you got 8,4Be, you can add another 4,2He, and that'll make 12,6C, carbon. So once you've got your heliums, you can put two heliums together, make a beryllium, get that beryllium, smash another helium into it, you get your carbon. And then everyone's happy. Now where do we go from here? Well, alright, so the deal is, our sun will last another 5 billion years, and then it will have consumed all of the hydrogen in the core. Basically, the hydrogen runs out, and everything starts to contract, but there's still hydrogen on the edge of the core. So that hydrogen, due to the contraction, begins to fuse itself, which puts positive radiative pressure on the star again and pushes everything out, whereupon the sun will become a red giant and consume Mercury and Venus. And of course, it's going to roast planet Earth, but it won't be a concern because we would have all evolved into pure energy creatures by that point. Now, the core will continue to collapse even though you've got the red giant aspect. And as the core continues to collapse, it'll eventually get to a point where it generates enough heat to fuse helium. This is called a helium flash, and it releases a huge amount of energy. And the helium will fuse in the core through the process that I showed you before, the triple alpha process, until it gets to a point where it starts to run out and become all carbon. And it will start to contract again, and as the core contracts, the helium that's not in the center, because that's all become carbon, but the helium on the outside will start to fuse, and that will push out the outer layers of the sun, so it becomes a red giant again. And basically, the helium in the core will continue to contract, and then any residual helium in there will begin to fuse again. And it will pulse in and out like this every 10,000 years, throwing off all the elements into the into space, making a planetary nebula, until all that's left is a glowing white-hot white dwarf made of carbon. And that will be what our sun will become. It will become a white dwarf. And it's not something that we currently need to concern ourselves with. You should be right. I don't expect the sun to be a red giant anytime soon. And if it does, you won't know about it for very long, I'm sure. Excellent. Enjoy your videos on neutrinos and have a wonderful weekend.